Hello everyone, I'm Guanghong from Purdue University. I'm going to present our paper titled Trace Divergence Analysis and Embedding Regulation for Debugging Recurrent Neural Networks. This is a joint work from Purdue University and Rutgers University. In software engineering, we have a lot of artifacts that are in the form of text or sequences, such as code comments, user reviews. We utilize those artifacts to assist software development or maintenance. Recurrent neural networks are widely used machine learning models that can deal with those inputs. Here is an example. Sentence strength is a tool using machine learning models to predict sentiments. The follow-up work utilizes this tool to extract problematic API features based on negative sentiment predictions. However, a recent study shows that sentence strength has very low performance on negative sentences, which can negatively impact downstream applications. Hence, in this paper, we aim to debug RNN models for better performance. A typical textual application usually takes in a text sequence and produces a desired output. Text sequence consists of a list of words, which are first transformed toward embeddings before fed to an RNN model. Existing studies show that word embeddings are a dominating factor for performance of RNN models. Different embeddings can lead to significantly different accuracy, from 63% to 89% with the same model. We hence focus on fixing bugs caused by problematic word embeddings in this work. Neighboring words can be used to measure the quality of word embeddings. For target word error, we list its neighboring words using the original embedding. We can see that word correct is very close to word error, which is not desired when it comes to sentiment analysis applications. The regulated column shows the results of regulated embeddings. We can see that word correct goes down on the list. Here is another example. The target word is reinstall. Our regulated embeddings move related word install up on the list. Although embeddings seem external to the model itself cannot be studied separately without considering embeddings. As such, we treat them as a whole during bug fixing. Suppose we try to debug an RNN model whose code implementation is in the following. The task of this code is to produce some label given an input sentence. There is a loop in the code. We show the RNN model on the right and also unroll the loop to individual steps. Each step computes the equations in the box, which are mathematical representations of line 8 and line 9. xt is a word embedding, ht is a history vector, and ot is an output at each step. We say each pair of input, including internal and output, is a state, and all those states constitute a trace. The last output is the final prediction. Line 6 maps individual words to their corresponding embeddings. In the following slides, we will show how to utilize state vectors and their trace to identify root cause of misclassification. A misclassification is due to some buggy internal states in a trace. We use an example sentence to explain our analysis. Word also is first transformed to its embedding and then fed to the model, which produces an output for current step. The input, history, and output constitute the state vector. It is the same for the next word and the following. Those states along the time step compose a trace. We collect those state vectors as inputs and outputs, and then train classifiers on validation set to identify divergent steps. Please find the details of constructing those classifiers in our paper. Here are the output traces produced by the classifiers along the time step. We can see the two traces diverge at word match, which means the state is problematic at this time step. Problematic state dimensions are the root cause of buggy states, which leads to misclassification. We aim to identify and fix those dimensions. We use the same example from previous slide. For a divergence step, we first obtain its state vector, and then we times it with a pre-trained importance vector. Those dimensions with large values are the defective dimensions of buggy states, because they are more important to the classification results. Finally, we aggregate defective dimensions from all the divergent steps. From our previous analysis, we know that the presence of misclassification is due to the sensitivity of model on defective dimensions. We hence aim to reduce such a sensitivity by regulating word embeddings. We've identified the defective dimensions in the previous slide. Here, we add random perturbations on those dimensions. Now, we have an original state vector and a perturbed version. Different from traditional training procedure, we freeze model parameters, and we use the output difference from two sets of state vectors to regulate embeddings. Finally, we retrain the model using regulated word embeddings. Please find the details in algorithm 2 in our paper. We evaluate our technique trader on 135 models and can improve model accuracy for 5.37% on average. We also conduct a case study on model behaviors. Red color denotes negative sentiment, green denotes neutral, and blue denotes positive. The ground truth is on the left. The right part shows two example sentences. Sentences in the top rows are produced by the original model, and the bottom rows by the fixed model. We can see that fixed model can produce negative sentiment of word work in presence of word not, whereas the original model cannot. Our artifacts are available on GitHub. Our technique is related to other existing model debugging work. Due to time limit, I will skip this. Please see our paper for the detailed discussion. Thank you.